Welcome to Introduction to Geology. I'm Dr. William Patterson. In this module, I'll be discussing the geothermal gradient and the evolution of the geodynamo, how it directs our turtles and pigeons on where to go. An understanding of the Earth's interior includes an understanding of the geothermal gradient, the increase in temperature with depth within the Earth's interior. Pressure and temperature are going to determine the state of matter, whether it's molten or solid, how viscous that material is, therefore its resistance to flow, and how its atoms are packed together in crystals. The curve that describes how temperature increases with depth is called the geotherm, basically Earth temperature. This figure compares a possible geotherm in yellow with the melting curve for the mantle and core material in red. These melting curves demonstrate how melting is dependent upon pressure, which increases with depth. At the Earth's surface, it's easy to measure temperature. We can do this down to depths of about 4 kilometers in mines and about 10 kilometers in boreholes. What heat flow modelers have found is that the geothermal gradient is 20 degrees to 30 degrees per kilometer in most continental crust. Conditions below the crust are inferred from properties of lavas and rocks emitted by volcanoes. That data indicates that temperatures near the base of the lithosphere ranges from around 1300 degrees to 1400 degrees centigrade. At these temperatures, the geotherm rises above the melting point of mantle rock. This geotherm intersects the melting curve at about 100 kilometers depth beneath most oceanic crust, and a bit deeper, 150 to 200 kilometers beneath most continental crust. From this point to where the geotherm drops below the melting curve at depths of 200 to 250 kilometers, the mantle material is partially molten. This observation is consistent with the existence of a shear wave low velocity zone, as well as with the widespread evidence that suggests that these basaltic magmas are produced by partial melting in the upper part of the asthenosphere. The steep geothermal gradient at the Earth's surface tells us that the heat is transported through the lithosphere by conduction. Below the lithosphere, the temperature does not rise as rapidly. If it did, temperatures in the deeper parts of the mantle would be so high that the lower mantle would be entirely molten. That is not consistent with seismological observations. Alternatively, the change in temperature with depth drops to about 0.5 degrees centigrade per kilometer, which is the geothermal gradient expected within a convecting mantle. This decrease occurs because convection mixes cooler material near the top of the mantle with warmer material at greater depths, thereby averaging out the temperature differences. Phase changes that are seen as steep increases in seismic wave velocities appear in the transition zone at depths of 410 and 660 kilometers. Seismology can accurately determine these depths, and therefore pressure, at these phase changes, such that the temperatures at which the phase change take place can be calibrated using high-pressure laboratory experiments. The numbers obtained from these laboratory data are consistent with the geotherm shown in this figure. Although we have more limited information about temperatures at greater depth, most geologists agree that convection extends throughout the mantle, vertically mixing material and keeping the geothermal gradient relatively low. However, near the base of the mantle, we expect temperatures to increase more rapidly because the core mantle boundary restricts vertical mixing. Convective movements near the core mantle boundary, similar to those near the crust, are primarily horizontal rather than vertical. Heat is transported from the core into the mantle through this boundary layer predominantly by conduction. The rate at which this heat is transported is proportional to the geothermal gradient. To transport the heat fast enough, this gradient must be significantly higher, similar to that in the lithosphere, 20 to 30 degrees per kilometer. Seismology indicates that the outer core is liquid. This means the temperature is high enough to melt the iron alloy that makes it up. Laboratory data indicate that this temperature is probably greater than 3,000 degrees centigrade, and that estimate is consistent with the high geothermal gradient at the base of the mantle as predicted by convection models. On the other hand, the inner core is solid. Because its iron-nickel composition is nearly the same as that of the outer core, the boundary between the inner core and the outer core should correspond to the depth where the geotherm crosses the melting curve for core material. This hypothesis implies that the temperature at the Earth's center is slightly less than 5,000 degrees centigrade. Some geologists, however, believe that the Earth's center may be as high as 6,000 to 7,000 degrees centigrade. Seismic tomography is an adaptation of a medical technology called CAT scanning, or computerized axial tomography. In the case of seismology, geologists use the travel times of seismic waves from earthquakes, as recorded on thousands of seismographs around the world, to sweep the Earth's interior in many different directions and construct a three-dimensional image of what's inside. One hypothesis would be that regions where seismic waves speed up are composed of relatively cool, dense rock, like a subducted lithospheric plate, whereas regions where seismic waves slow down are composed of relatively hot, buoyant rock, such as in a mantle plume. Seismic tomography has revealed features in the mantle that are associated very clearly with mantle convection. Researchers at Harvard constructed a tomographic model of the mantle. This model depicted here is a cross-section of Earth and a series of global maps at depths ranging from just below the crust down to the core mantle boundary. Near the Earth's surface, you can clearly see the structures of plate tectonics. The upwelling of hot mantle material along mid-ocean ridges is visible in warm colors. The cold lithosphere in old ocean basins and beneath the continental crust is visible as cooler colors. As depth increases, features become more variable and less coherent with surface tectonic features. Some large-scale features stand out particularly well. You'll notice that just above the core mantle boundary, there's a red region of relatively low S-wave velocities beneath the central Pacific Ocean, surrounded by a broad blue ring of higher S-wave velocities. Seismologists speculate that the high velocities represent a graveyard of cold oceanic lithosphere subducted beneath the Pacific's volcanic island arcs and mountain belts, known as the Ring of Fire. This happened during the last 100 million years or so. The cross-section through the mantle clearly reveals material from the once large Farallon plate, which has been almost completely subducted under North America. This obliquely sinking slab material, shown here in blue, appears to have penetrated the entire mantle. The image also indicates sinking colder rock beneath Indonesia, another subduction zone. Additionally, a large yellow blob of hotter rock, thought to be a superplume, can be seen rising at an angle from the core mantle boundary to a position beneath southern Africa. This hot buoyant mass is pushing up cooler material above it. This may explain the uplifted mile-high plateaus of South Africa. The other visible blobs of hotter and cooler material may be evidence of material exchanges among the lithosphere, the mantle, and the layer of hotter material at the core mantle boundary. The same temperature variability that speeds up and slows down seismic waves also plays a role in determining the density of mantle rocks. Laboratory experiments have demonstrated that the expansion of rock caused by a 300-degree increase in temperature reduces its density by about 1%. Although this seems trivial, the mass of the Earth's mantle is ginormous, about 4 billion trillion tons. So even small changes in the distribution of its mass can lead to observable variations in the pull of Earth's gravity. Like the mantle, Earth's outer core transports most of its heat by convection. The same techniques that have revealed so much about mantle convection, seismic tomography, and the study of Earth's gravitational field have provided almost zero information about convection in the core. Why hasn't it? The problem has to do with fluidity of the outer core. The mantle is a viscous solid that flows very slowly. As a result, convection creates regions where temperatures are significantly higher or lower than the average mantle geotherm. We can see in this figure places where seismic wave velocities are lower or higher than the average for that depth. The outer core, in contrast, has a very low viscosity. Its molten material can flow as easily as water or liquid mercury. Even small density variations caused by convection are quickly smoothed out by the rapid flow under the force of gravity. Any lateral variability in seismic wave velocity caused by convection will be too small for us to see using seismic tomography, and they will not cause measurable distortions in the shape of the planet. However, we can investigate convection in the outer core through observations of Earth's magnetic field. You can refer to the modules on Introduction to Geology and the modules on plate tectonics for a little bit of a background on that. The most basic instrument used for measuring Earth's magnetic field is a simple compass, invented by the Chinese more than 2,000 years ago. For hundreds of years, explorers and ship captains used magnetic compasses to navigate, but they had little understanding of how these ancient devices work. In 1600, William Gilbert, Queen Elizabeth I's doctor, provided a scientific explanation. He proposed that the entire Earth is itself a great magnet, whose fields act on the small magnet of the compass to align it in the direction of the North Magnetic Pole. Scientists of the 1600s had begun to visualize a magnetic field as lines of force, such as those revealed by the alignment of iron filings on a piece of paper above a bar magnet. Gilbert demonstrated that the Earth's magnetic field lines point to the ground at the North Magnetic Pole and outward at the South Magnetic Pole, as if a powerful bar magnet was located at the Earth's center and oriented with an axis inclined about 11 degrees from Earth's axis of rotation. What this means is the lines of force reveal a dipole, two-pole magnetic field. And this is how Gilbert solved an important problem for a nation that was dependent upon the compass for maintaining its empire around the world. But he was only partially correct. We now know that the source of the magnetic field is a geodynamo powered by core convection, not a permanent magnet at the Earth's center, which would be quickly destroyed by high temperatures. This geodynamo is formed by rapid convective movements in the liquid iron-rich electrically conducting outer core. The magnetic field produced by the geodynamo is considerably more complex than a simple dipole field, and it is constantly changing over time due to these fluid movements. Only a few decades after Gilbert made this hypothesis known, careful observations revealed that the magnetic field varies over time. It's no surprise that some of the best evidence for these changes came from compass measurements systematically recorded by the British Navy as they ruled the world. Navigators had to correct their compass bearings to account for displacement of the Earth's north magnetic pole from the rotational pole, the magnetic pole being the magnetic north and the rotational pole being the true north. These corrections demonstrated that the north magnetic pole was moving at rates of 5 degrees to 10 degrees per century. Secular variation in the Earth's magnetic field for the last 300 years, mostly from the British Navy, demonstrate that both the dipole and the non-dipole components of Earth's magnetic field are changing over time, but that this secular or time-related variation is most rapid for the non-dipole component. Secular variation is evident when we compare a map of today's magnetic field at the core mantle boundary with maps reconstructed for previous centuries. Changes in field strength occur at timescales of decades and indicate that fluid movements within the geodynamo are on the order of millimeters per second. Scientists can use this secular variability to help them understand convection in the outer core. Now that our computers are super, we've been able to simulate the complex convective movements and electromagnetic interactions in the outer core that might be creating this geodynamo. These same supercomputer simulations also allow us to understand the behavior of the geodynamo in terms of spontaneous reversals of the magnetic field. As we mentioned in our modules on plate tectonics, the magnetic field reverses its direction at irregular intervals ranging from tens of thousands to millions of years. In one of those events, the North and South Pole reverse. Computer simulations of this phenomenon have indicated that there may not be an external trigger required for a magnetic field to reverse. It just happens spontaneously, purely through internal interactions with the Earth's core. The geodynamo here is a self-organized natural system, one whose behavior is not predetermined by external constraints, but emerges from interactions within the system. We've seen in previous modules how the geologic record of ancient magnetism, or paleomagnetism, has provided critical information for understanding Earth's history. Magnetic anomalies mapped on the ocean crust confirm the existence of seafloor spreading and provide the best data for tracking plate movements since the breakup of Pangaea 200 million years ago. Paleomagnetic data from old continental rocks has been essential for reconstructing earlier supercontinents, such as Pangaea and Rodinia. Scientists have also used paleomagnetic data to reconstruct the history of the Earth's magnetic field. The oldest magnetized rocks found thus far formed about 3.5 billion years ago, indicating that the Earth had a magnetic field similar to the present one 3.5 billion years ago. The presence of magnetization of most ancient rocks is also consistent with ideas about Earth's differentiation, that a convecting liquid core must have been established very early in Earth's 4.5 billion year history. In the early 1960s, a graduate student in Australia found a fireplace in a campsite where Aboriginals had cooked their meals. He noted their physical orientation, then he measured the direction of the stone's magnetization and found that it was exactly the reverse of the Earth's present magnetic field. He proposed that as recently as 30,000 years ago, when the campsite was occupied, the direction of the magnetic field was the reverse of the present one. That is, a compass needle would have pointed south rather than north. Now, this requires that we remember that high temperatures destroy magnetization. A critical property of many magnetizable materials is that as they cool below around 500 degrees, the carry point, they become magnetized in the direction of the surrounding magnetic field. This happens because groups of atoms of the material align themselves in the direction of the magnetic field when their material is hot. When the material cools off, these atoms are locked in place. This process is called thermoremnant magnetization because the magnetization caused by heating and cooling is remembered by the rock long after the magnetizing field has disappeared. Thus, the Australian student was able to determine the direction of the Earth's magnetic field at the time the stones cooled after the last campfire. Thermoremnant magnetization is exactly the same process that magnetizes lava flows in newly formed ocean crust. Discovery of magnetic reversals in igneous rocks was a key ingredient for the formulation of plate tectonics theory. Some sedimentary rocks can take on a different type of remnant magnetization. In the case of marine sedimentary rocks that form when particles of sediment have settled to the seafloor and become lithified, magnetic grains may be among those particles. Such magnetic grains, like magnetite, become aligned in the direction of the Earth's magnetic field as they fall through the water, and this orientation may be incorporated into the rock when the sediment becomes lithified. This is depositional remnant magnetization found in some sedimentary rocks, resulting from the parallel alignment of all these tiny little magnets. Paleomagnetic stratigraphy relies on these reversals, particularly over the last 170 million years. From the rock record, we know that the geodynamo began to operate early in Earth's history, and that life therefore evolved within a strong magnetic field. The consequences turn out to be rather surprising. For example, many organisms, such as turtles, pigeons, whales, and even bacteria, have evolved sensory systems that use the magnetic field for navigation. Their basic sensors are small crystals of magnetite that have become magnetized by the Earth's magnetic field as they are biologically precipitated within the organisms. These crystals act as tiny compasses to orient the organism within the magnetic field. Geobiologists have discovered that some animals can use arrays of magnetite crystals to sense the strength of the magnetic field, providing them with additional information for navigation. A recent study has indicated that iron atoms in macrophages, very tiny microorganisms that eat damaged cells, the iron atoms in those macrophages are used in the livers of pigeons to help them navigate. I'll just leave it at that. The magnetic field is not just a convenient frame of reference for flying and swimming species. It's part of the Earth system, essential for sustaining a rich and delicate biosphere at the planet's surface. Although the geodynamo forms deep within the Earth, its effects spread out into space and actually protect the Earth's biosphere from damaging ionizing radiation. Without it, we're all in trouble.
You gotta keep the devil down in the hole. He's got the fire and the fury and his